Well, hello, ladies and gentlemen, and today we're going to have a demonstration that helps illustrate how physical and chemical properties can help define the elements that we're looking at. Now, yesterday we watched a video that helped to explain what physical and chemical properties are. And if you remember, the physical properties are properties that we use our five senses for to be able to describe. Is it hard? Does it taste good? Does it have an odor? How does it look? What's its color? Does it sink? Does it float? What's its mass? How does it go through the air? All these things we're able to use our five senses for. And we've learned from those physical properties that whether or not that's good for us. For example, let's think about an apple. Okay, we're sitting there, we see this red roundish thing. Okay, two physical properties. You bite into it, it has a sweet taste to it. Again, physical properties. But that's how the chemicals are reacting. Chemicals are reacting so that our taste buds are able to read it as a sweet taste. It has a sugar inside of it that we really appreciate. Now, we're going to not look at fruits and foods. Instead, we're going to look at metals. And normally when you think about metals, you're like, oh, look, it's shiny, it's silver. I know everything that there is to know about metals. If I throw it in the water, bloop, 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 it sinks. So we can figure out the density where we compare its mass to its volume. We can take its mass. We can see if we can get enough heat and see if we can melt it. See if we can turn it red. And then we can be able to melt it and or bend it and put it into different shapes, which is basically how we got the shape of this butter knife. Did the same thing in order to get this fire extinguisher. We also know that metals are hard. Normally we don't want to hit ourselves with a metal because it's so hard. I usually can't cut through it. I bet you can see what I'm going to be leading up to. We're not going to be working with these metals. Things like iron, tin, they're towards the center of the periodic table. They're not very reactive. They're usually found in ores. They can be melted out, separated, and we can use them in order to give us these solid masses. Okay? Instead, we're using something that is rarely, if ever, found in nature by itself because they are so highly reactive. These are called alkali metals. The alkali metals that we're using are going to be lithium, sodium, and potassium. Now, on quick inspection, you're going to say, well, I don't know, they really look like metals. Well, it has a hardness to it, but they didn't really have the color. You know, that's not really what we would expect, especially if I look at sodium. Sodium's kind of a whitish color, kind of, you know, weird shapes, everything else. You know, maybe not so much a metal. Well, I'm telling you, they're actually metals. And since they're all the way to the left of the periodic table, they have one electron. And that one electron really wants to escape. And that's what makes this a fun demonstration, because since they want to escape, it makes them highly reactive, especially to water. Okay. So with that being said, let's go ahead and talk about our learning goal. Since we're using alkali metals, you should be able to elaborate on the physical and chemical properties through the demonstration of the alkali metal family. That's right, these are all in a family. When we look at the vertical alignment, these are called families. So in group 1, these all are going to have similarities, just like your family at home. Even though you don't look the same, you may not always act the same, but there's similarities. Maybe it's eye color, hair color, maybe it's your height, maybe it's the music that you like, it's the foods you like. There's similarities. They're not always going to be super evident, but they're there. Okay? Now, since these are so highly reactive, we have some safety precautions we have to take. First is for you. You'll notice that you're standing behind a line. This line says student line. You are not to come in front of that line. This gives me a buffer. As it states here, I have spatial precautions. This buffer is 8 feet. So you have 8 feet from your line to the front of this counter. And then if something were to happen to me, then you have another 3 feet to be able to get to me. This is because I don't want you touching me or anything else like that if something does occur. I'm not saying it has. I've been around for a long time doing this, and nothing has happened to me yet. But that doesn't mean that it can't happen. That's why they're called accidents, and they happen. Okay. The protective equipment. You all came in here, even though it's a demonstration, we had you lab appropriate. Since you are lab appropriate, that means that you have socks on, shoes on, long pants, hopefully jeans. You have short sleeve shirt, not too baggy. This is to protect you just in case something does go a little bit wrong. And usually, if you're lab appropriate, that takes care of just about everything. Okay. Next, the hazard aspects of the activity. What exactly does that mean? Well, it means stuff can blow up. That's why we're here. We're having fun. Hopefully, we won't get too big of an explosion, even though I know that's what you're hoping for. We should be able to control it, understanding what we're working with. That's why I'm working with it and you're not. And access to and operation of safety equipment. Okay. Now, not only am I lab appropriate, but I have other safety equipment with me. First, for personal protection, the MSDS here told me that I need to wear gloves. It makes sense. As a human, I'm mostly water. Since I'm mostly water, and I just told you that this stuff likes to react with water, I need to make sure that my skin doesn't touch this, or else I'm going to be in a lot of trouble and not have a very good day. Same thing for my eyes. I need eye protection. If I'm not protecting my eyes, then I'm not doing myself a very good service. Okay, we're very visual creatures. If something gets into my eye, I can lose my vision. I want to use the goggles, even though you may say, hey, they're not the best looking things in the world. They leave marks on my head. We still want to use the goggles. Okay. Also, I'm wearing, I hope, a non-flammable lab coat. I don't want to find out if it's true or not, but manufacturer label says that it is. It's just an extra layer of protection in case something does land on me and I don't get burned. Now, not only do I have that, but I have this nifty fire extinguisher. But Mr. Pierce, you may say, this stuff's supposed to react to water. Well, this one doesn't have water in it. It's a non-water chemical. It's a class M. It's meant for things that may react to water. See, thinking ahead. We also have sand. So for some reason something huge goes on, I can pour sand onto it. Sand is one of the driest materials out there. But there's an instance where I may need water. According to the MSDS, if I get a little bit on my skin or if I get something called a residue, which is a little bit that's left over, then I should rinse off in the wash station for 15 minutes. And then if I need extra help, I need to call first aid. So, all right. Now we understand what we're working with. Okay, so let me backtrack just a little bit. We do understand what we're working with, but what about when we're all done? Well, this stuff has to be disposed of. I'm making new chemicals because, like I said, they're reactive. Here I'm making lithium hydroxide, and I said it's corrosive to skin, so I'm pretty sure I'm not going to drink it, and I'm not just going to go ahead and throw it out to where any animal can get it. It has to be specially contained. Sodium hydroxide, also known as lye, very corrosive, and potassium hydroxide, well, as I'm going up, it's more reactive. You can just figure out that's probably worse off than the other two. We have special containment systems. We're able to put this down to the down sink as long as we dilute it. So that is the plan for these materials. Anything that's left over gets put back into the containers where there's an oil so that it's not exposed to any kind of humidity, and I get a big boom in the storage room. Okay. Also, these are kept in a can that has sand inside of it, so that any kind of excess water is actually trapped that way as well. So we're covered on all ends. So let's see if we can do this demonstration. As I don my goggles, we are now in science mode. All right. First, lithium. We take a look at it. I talked about metals being able to rust. Right now it has a blackish color. What color do we normally expect metals to be? Oh, shiny and silver. Not so. But watch. If I go ahead and cut this, and yes, I am using a butter knife to be able to cut this, and poof, I've cut it. So there's a little bit of hardness to it, but if I tried to do that with the fire extinguisher, I'd be there for a while, and I'd probably end up hurting myself. This was actually pretty easy to cut, pretty easy access. Now, like I said, black right now. Oxidation. Chemical property, it reacts to air. I turn it around, notice, shiny. We all like shiny objects. So, shiny side, now that looks more like a metal. Metals, they normally react in water. Let's go ahead and get a little bit of a smaller piece, and we're going to see what happens. Now this one doesn't have very many electrons, so do you think it's going to be super reactive to water? It's going to be pretty reactive to water, but probably not as exciting as you may think. So let's see. It's almost like an Alka-Seltzer tablet. We have some gas, we got some bubbles, but look, the metal's dancing. That's pretty cool. So with the gas coming, we have the bubbles, which let us know that gas is actually being produced. Lets us know there's a chemical reaction occurring. This lets us know that the chemical property of lithium reacting with water is actually occurring. So we don't have any kind of color change, but we see that it's disappearing. This isn't dissolving. This is totally different than if I put sugar into water. Instead, this is a reaction. And with the reaction, I'm getting a totally new substance. Unlike sugar water, if I allow that water to evaporate, I'll find a sugar on the side of the cup. You all have done it. I know that you found a cup of Kool-Aid in your room, and you saw that all the dye or all the purple color, and it was grainy in there, even though all the water was gone. That's because now you have the Kool-Aid. You add water to it again, you got Kool-Aid again. This one, not so. I can't separate this anymore. I can't get just lithium unless I use a special process. New physical and chemical properties, now corrosive to the skin. All right, next, sodium. You're going to say, well, sodium, isn't that in table salt? Well, yes, it is in table salt. However, if I take a big old chunk of this, probably my mouth's going to explode. And since I'm not a dragon, that's not going to be a good thing. So, with the sodium here, it needs to react with something else. It's going to, for table salt, we have it react with chlorine. Chlorine and sodium, both very bad to humans. But you put it together, it makes a tasty treat. We all use salt. In fact, our bodies don't work if we don't have sodium and chlorine atoms inside of our body. We use those ions as things that allow our muscles to work and for our nerves to work. It's pretty amazing that we need this kind of stuff inside of our bodies and how it works when it's not in these different forms. Okay. Physical property. Right now you see it's white. Looks a little different than lithium, doesn't it? Black, white. Well, like I said, there's similarities. That's its tarnish. This tarnished as well. It rusted. Both oxidized, both are reactive to air. Notice I was able to cut this with a knife. This, oh man, that was even better. Now if we take a look inside, shiny. Let's see, not shiny. Shiny. So again, this looks like a metal, just like the lithium that we cut into. Similarity, because it's in the same family. Now another similarity, it reacts to water. Let's take a look and see what happens. And very malleable. So I'm able to move it into a different shape. Sodium has a few more electrons, so sometimes we can get a bit of a flame, sometimes it doesn't. It just does a really cool dance. Notice, large container, only half full. That helps contain if there is any kind of flame or anything else like that, so it doesn't get out everywhere else. So let's see what happens. As soon as I put it in the water, we have a reaction. We have a lot of gas coming out. Again, we can see that because there's so much bubbling, it actually dances in the water. Really cool to look at. And sometimes if we get lucky, we can get a nice little flame towards the end because there's so much electrons trying to get out, and it wants to go so quickly. And because the water actually starts getting into the inside, we get a pop from the inside out. I just think I'm getting so good at this that I don't get the pop anymore. But again, reactivity, we know that's happening. Not dissolving, it's reacting. If I were to go ahead and put something in there, it would actually start corroding. I can actually get color, paper to this color, putting it into this, this new substance. Excuse me. So again, pretty cool. We get to see that the item is actually dancing. We see that a reaction is actually occurring. It's not dissolving. It's reacting. I'm getting something totally new. And now finally, this one is kind of fun. Now we've noticed these others, they had a lot of tarnish. This one doesn't tarnish as much. Okay, so we see a lot more silver color. So I don't even have to cut into it. I'm not even going to use a knife. This is almost like pulling apart bubble gum. So really kind of cool. Okay, this is potassium. We've all had potassium. You bite into a banana, you have potassium. And no, if you put banana in the water, it's not going to explode. Okay, if you put Special K in the water, it's not going to explode. It's because it's in a salt form. We just talked with here with sodium, salts have different physical and chemical properties. Okay, this is in its pure form. You're very rarely going to find this in its pure form. Again, the body needs this. We need potassium. If you've ever had a Charlie horse, it's usually because you don't have enough potassium and your muscles go ahead and contract very hard. Also helps with the retention of water. All right, so with this is even bigger, has more electrons. Let's see what happens when I put this into water. Watch the color of the flame. Watch how quickly it does react. As soon as I put it in there, we got a flame. We have a lot more gas. You can hear a lot more sizzle. And it's excellent. That was just awesome. All right. So hopefully, by looking at all this, we now have new substances, new physical properties, new chemical properties. Clear, clear, clear. All similar. They're all bases, all corrosive, but started from something totally different and something that's considered a metal. Thank you.